If you throw a small object at a wall, you would expect it to bounce back and not go through the wall, unless of course it was a bullet. But in quantum mechanics, this happens all the time. In our day-to-day life, if an object doesn't have enough energy to cross a barrier, it won't cross it. But in quantum mechanics, it can simply tunnel through the barrier. This can be explained using wave-particle duality, wherein a fundamental particle can exhibit properties of both waves and particles simultaneously. The wave nature determines how delocalized a particle is. The wave nature is given by the de Broglie wavelength. For an electron, the mass is extremely small, which gives it a significant wavelength, whereas normal objects have much larger masses, which makes them have ridiculously small wave natures. So quantum mechanical effects can be ignored for these particles, and we use classical approximations. An example of a free particle, say an electron, can be taken wherein it encounters a barrier. These barriers are commonly called as potential barriers, where the vertical height represents the potential. We can divide this diagram of the electron into three regions. In region 1 it is incident, in region 2 it is in the barrier, and in region 3 we have the particle exiting the barrier. Since we talked about wave-particle duality, this particle can be represented using a wave function which describes its state. These wave functions are derived using the Schrödinger equation. This is the general form of one. Here U represents the potential. Now in region 1 we have a free particle which is not bound to anything, so its potential is 0. This is the Schrödinger equation in region 1. This is the Schrödinger equation in region 2. And again the electron is free in region 3, so this is its Schrödinger equation. Here psi1, psi2 and psi3 are separate wave functions in each region. The solution of each Schrödinger equation can be found by solving the second order differential equation in each region separately. In region 1, we have this general solution that can also be represented through this equation, which is an oscillating function. Here A is the amplitude of the incident wave and B is the amplitude of the reflected wave. This is the graph of the wave function in the first region. Now in region 2, this is the solution for the wave function. Over here we have an exponentially decaying wave function, which means that the wave function decays exponentially within the barrier region, and this is the graph of the wave function. In region 3, the solution is again an oscillatory function, but this time the wave function exits the barrier and travels freely into space, so the component of the reflected wave, that is G, is 0. And this is the final solution in the third region. This is the graph of the wave function in the third region. Its amplitude is much lesser than the oscillating wave function in the first region. This is due to the fact that the wave function exponentially decays within the barrier, which causes the amplitude to decrease. Now, the entire solution can be given using this diagram. Earlier we had three regions for a free particle. We can now divide this new diagram into the same three regions, but instead we see the particle as its wave function. The probability of the particle actually tunneling through the barrier is proportional to the ratio of the squares of the amplitudes of the wave functions. This depends mainly on the width of the barrier. If the width of the barrier is greater, then the chance of tunneling is lesser, and vice versa. This can be seen through the simulation.